All right, everyone, Mr. Graham here. Today I want to give you just some demonstrations about electromagnetism, the kind of stuff we've been talking about the last several days. I know it's kind of hard to visualize a lot of this stuff in our brains because a lot of it's invisible. Magnetic fields are invisible. Electric currents are kind of invisible unless you got sparks. So I want to give you just some hands-on, not really hands-on, some eyes-on demonstrations of what all this stuff is. I know Mr. Luis and you might have seen some of this already, so this might be kind of a review for you, but I'm going to talk about some of the basics and then go on to talk about some of the devices that we use to harness electromagnetic properties to generate things like electricity, which we like. First thing I want to talk about is that magnets have been known about for literally thousands of years. The ancient Chinese were the first ones, at least from my recollection, that used naturally magnetic rocks in order to make little magnetic needles to make compasses. And compasses have been used forever to navigate. You can't really navigate across an ocean without the use of a compass. So the reliance on magnetism for global travel, that was pretty huge. So naturally occurring magnets, they're actually rocks like this guy. Sorry. I'm going to be zooming in, zooming out, turning the lights off, so it's going to be kind of annoying. So just to warn you about that. So this is a rock commonly called a lodestone, Lodestone, and it's naturally magnetic. And what happens is that when you have an iron-rich composition in a magma, when it solidifies into a rock, those iron pieces of iron, those iron minerals, iron-rich minerals can align with the Earth's magnetic field as it cools and solidifies, and in the right conditions can form a magnet. Now, it's not going to be a strong magnet, usually. I got paper clips here, and I'm going to try to pick them up with my naturally occurring magnet. As you can see right there, so got some paper clips right there, and they don't get picked up. So it's a really weak magnet, but we know that it's magnetic because I do have a compass needle mounted on this guy right here that will get deflected if I bring my my lodestone close. So we can detect a magnetic field. It's just not going to be very useful for doing things, but moving very lightweight objects within the Earth's magnetic field, yeah. So hopefully that makes sense. So that's called a lodestone. The most common types of magnetic minerals that will actually form naturally occurring magnets are hematite or magnetite. Magnetite obviously gets the name from being magnets. I think I'm pressing the wrong button here. Oh well. And so magnetite is spelled magnetite. Magnetite is the most common one. Hematite. There's also another one. Both of those are naturally magnetic minerals, and when those minerals accumulate within a rock, they can form a magnetic rock. Good. All right. Now, to get a bar magnet, a permanent magnet, otherwise any permanent magnet, to get a permanent magnet, these aren't naturally occurring. We actually have to create those. Now, how do we create those? Well, we use electricity. You know now that electricity and magnetism are inextricably linked together. And so how do we form permanent magnets? We use something like this. It's called a magnetizer. And so this is used to strengthen magnetic fields or strengthen magnets. But the same principle can be used to actually create magnets. So what you do is just put the north end of one magnet, north pole of one magnet in here, the south pole in the other one, and then connect them so an electric current can actually run between them. And then you run a high current electricity through it, maybe once or twice, and then we have a strong magnet. So these guys are noticeably stronger now that I brought them out than they were when I put them. So that's that is an artificial magnet that we can create, that people can create. And obviously it's going to be magnetic. Let me switch it back, because I can pick up these paper clips with the magnet. Okay. All right, magnetic field lines. It's all about the magnetic field lines. If you go on to become a physicist, if you go on to learn calculus-based physics, when you go to college or when you take AP Physics C next year, The magnetic field is the important thing. The magnetic and electric fields, the way they interplay with each other, is very important. And so we should know at this point that the magnetic fields make these, if this is the north pole of the magnet and that's the south pole, the magnetic fields make these kind of shapes. You know, hopefully we knew this already before we took physics in high school. You should have learned about this a little bit in middle school, and then they go like that. And then just so physicists and electricians and electrical engineers are using the same mathematics, we have to define directions here. And so by definition, we just say that North Pole, the magnetic fields emanate from the North Pole, and then they enter the South Pole. So I can indicate that with little arrows. Right. So that's the direction of magnetic field lines. And I like to visualize them. I'm going to have to move the camera over here. But what I got here is a little container that's got iron filings in it, just little pieces of iron that aren't magnets in and of themselves, but they feel magnetic forces. And it's suspended in a fluid. And so what I can do is just put that on a piece of paper so you can see it a little better, and just place a magnet on top and give it a little shake. Give it a little shake, and then we should be able to see those iron filings line up with the magnetic fields. Get that to look a little better. There we go. And I'm going to have to lift the camera up to show you this, so hopefully it'll work. Hopefully it won't get too... Uh-oh. So I hope we're seeing this here. Okay. So there, hopefully you can see those field lines, not the field lines themselves, they're invisible, but hopefully you can see the iron filings lining up with those field lines. Okay. And hopefully I don't unplug my camera while I'm doing this. All right. Nope, too far. Okay, so that's the direction of magnetic field lines. They point away from north and towards the south. Now, magnets aren't the only things that generate magnetic fields. We learned that actually all magnetic fields are generated, in fact, by electric currents, even within permanent magnets. And we watched a video on that, so I'm not going to explain that too much. But we know that current carrying wires, electricity flowing through a wire, if it's in the presence of a magnetic field, then it will actually feel a magnetic force. And I got a little demonstration to show you that as well. So let me just get this set up. I'll put this in the switch actually. So my setup here has, and this is going to be pretty subtle, and then I'll show you how we magnify this effect in actual devices that we actually use to do stuff for us. Bring this down. So let me zoom in so you can get a lot better look. All right. So what I have this wire that's going down here. The current's coming in through the top and going down. And then I have some neodymium magnets, some pretty strong magnets right here that are right in front of the wire. Now if I turn them away and I run current through the wire, which you won't be able to tell, but there's current now flowing through the wire. I hit the switch. Now there's not. Now there is. Now there's not. Nothing's happening. But if I take that magnet and I put it right in front, so now that current carrying wire has a magnetic field flowing through it. And so now whenever I flip the switch, I see the wire move. Okay, I see the wire move. And so that is a magnetic force. Okay. Notice that it's moving this way. Now what if I reverse the polarity of the magnet? So the one pole was pointing out, now another pole is pointing out, and when I make the current go through the wire, it actually feels a force pointing in the other direction. Okay. Now again, this isn't very useful because as you can see, it's a very small force. But what I can do to magnify that is take wire and wrap it around in a bunch of loops. The more loops I got, the more pronounced the effect will actually be. And so I'm going to turn these guys around, put them in the vicinity of this loop of wire. The more loops, essentially the more current you have flowing in the presence of the magnetic field. And so now when I run current from this side to this side, I should get a much more noticeable effect. So now whenever I hit the switch, I see a noticeable force, right? No electricity, electricity, okay? And again, if I reverse the direction of the magnetic field by just flipping the magnet around, then the force is in the opposite direction. And the right-hand rule tells you that. One of the 3 right-hand rules that you learned, okay? Tells you the direction. And again, that's why the magnetic field direction is so important. That's why we need to define a direction, because we need to know what direction the resulting magnetic force is going to be pointing in. All right. Zoom back out. Okay, so it should stand to reason, if you know a little physics, that if I can get forces on wires, Newton's third law says that I should also be able to get forces on magnets, electric forces on magnets. And that's how electrical generation, electrical power generation, that's how electric motors work. They use the interplay between the forces between magnets and current-carrying wires in order to generate, either generate electricity or generate motion, as I'll show you here in a second. Yeah, so a simple motor, you might have seen motors like this. If you got drones, you have little tiny motors that look like this, that you hook electricity up to it. This actually burned out. I couldn't find my actual motor, my actual small motor that works, so I do apologize for that. But it's a little tiny device that has magnets and coils of wire in it. When electricity goes through, you get spin. You get the motor to spin. And I don't know if you'll be able to see this. Let me zoom in as much as I can. But this is one of those magnets, or one of those motors that I've taken the cap off. And if you look inside, you see the red that you see in there, they're coils of wire that are wrapped around a piece of iron. And then along the outside, we have magnets. And so when we connect this guy to electricity, then the electricity will flow through the coils and feel a magnetic force. The problem is that we need, once we get that magnetic force, it's going to cause it to turn, but then it's going to cause it to stop. Once the coil and the magnet feel that attraction, the thing will spin until the north is attracting the south, and then it stops spinning. So what people figured out how to do a long time ago was design a very clever electrical device using just wires and conductors and insulators in order to force the circuit to constantly reverse the direction. So if you induce a magnetic field within a coil of wire, and you have a south pole of the magnet over here, well, the north pole of the coil of wire is going to swing over here until there's the attraction there. But then it's not going to spin anymore because it wants to be there. But if we could just reverse the direction of the current when it gets here, then it will then reverse polarity and become a north pole or become a south pole and then continue to spin because now it wants to be connected to the other side. And then after it goes through another 180 degrees, we want that polarity to switch again. And how do we switch the polarity? We switch the direction of the electric current. Now that's not easy to do if you have a battery, the current goes one way, and so you can't really just reverse the direction that the battery is producing current. So we use what is called a commutator. A commutator is what I drew here. A commutator has the positive, so this is like a wire connected to the positive terminal of a battery. This is the wire connected to the negative terminal, so we got positive voltage, negative voltage. The commutator itself can spin, so I'll show you an actual commutator here in a second, an actual demonstration motor here in a second. It's like a little thimble-looking guy that's made of metal mostly, but then it has some insulators right here. So as this spins, the direction of the current will actually be reversed. If I start here, this point here is at negative voltage. As it spins though, once it gets over to this side, it will reverse and we'll get positive voltage. on the commutator. And then we have the commutator itself attached to the output that will actually cause that's connected to the coils of wire. So as the commutator spins, we keep reversing the direction of the current through the coils of wire. And this happens very fast. Every time a motor spins 180 degrees, the electric current gets reversed. And as you'll see here, it happens very fast. So this is called a St. Louis motor, because I guess it was designed in St. Louis. It's not a motor that you can actually do anything with because it's really hard to connect things to it. Oop, having trouble here. So the commutator is, zoom in. The commutator is this guy right here, that thimble-looking guy. And then these are called brushes, these metal parts that make contact with it. And that's what the positive and negative voltage is. That's where the voltage source comes in. And so as this guy spins, as the motor spins, the direction of the current gets reversed in these coils of wire right here. And in these coils of wire, there's a piece of non-magnetized iron, but when electricity goes through the coils of wire, it generates the magnetic field. And then we have magnets on the sides here that will actually cause the attraction and the repulsion with the magnetized coils in order to cause the spin. And since the direction of the current constantly gets reversed, the polarity of these magnets doesn't change, but the polarity of the magnetized iron and the magnetic field generated by the coils, that polarity is constantly going to change. And so let's see this guy in action. I connect the voltage. Lost you. I connect my voltage here. And so the electrical connections travel down through those brushes, which make contact with the commutator. And when every time this spins 180 degrees, the direction of the current in these coils of wire gets reversed, reversing the direction of the magnetic field that's generated in the spinny part, which then will cause repulsion and attraction to the opposite end of the magnets, the permanent magnets that are in it. Any motor has permanent magnets within it, I guarantee it. All right, so let's see. There we go. So notice how fast it goes. Every 180 degrees, the current is changing direction within these coils of wire. So you can obviously tell this is happening many times per second. So many, many times per second, the direction of the electric current is being reversed. And that's that's the most basic motor. In real motors that we actually use to do stuff, they're designed for that electric current direction. The more often you can reverse that electric current direction, the more efficient the motor will be at converting electrical energy into mechanical energy, the spinny energy. And I forgot to pull it out, but so I had a ceiling fan that crapped out a year or two ago, and so I decided to take it apart. And so when you take the ceiling fan apart, should brought my crowbar. There we go. So when I take a look at this, it's a lot more complicated. I got a lot more coils of wire and a lot more of those brushes. And so each one of these connections here that's on the outside of where all these coils of wire are, the electric current reverses direction every time that passes. Every time that passes the electrical connections. And then so you get that spinning motion. But notice it's all about the coils of wire. It's all about the magnets and the electromagnetic force that we get between them. I brought this in. This was pretty not fortuitous as far as me having to buy a new one, but my pool pump went out about a week ago, so I had to order a new one and replace it. But this pool pump is just a motor. It's just a motor that this part spins when you connect it to the electricity. Something called an impeller is screwed on there, and then it's connected within the water system. And as the impeller spins, just like a jet ski impeller, when it spins, it makes the jet go forward. But when a pool pump impeller spins, it forces water out. It gathers water and forces out the other end. Hi there. And so that's what a pool pump does. But all it is is a motor, just like this motor. Just like this motor here. All it does is take electricity going in and it spins it. Okay. It's a little more complicated because this runs on alternating current that your house is wired up with. You got to be a lot safer because the electricity that runs this is a lot more dangerous than the electricity that runs this. But that's why you get a multimeter and you get a voltage tester to make sure that the electric current is not running while you're doing the wiring. But if we look inside of it, what you'll see are big coils of wire. All right, we got big coils of wire. And when electricity goes through those big coils of wire, then the center part called the rotor, the outer part called the stator. The stator houses the magnets. The rotor has the electric coils. Sorry, the stator houses the electric coils. The rotor has the magnets within it. And so the same process that makes this little St. Louis motor spin makes this guy spin. But this spins a lot faster and with a lot more energy. So it can pump, a few hundred or a few thousand gallons of water through your pool every minute. So, not thousands per minute, but a lot. Okay, so that's electric motors. What else? Okay. So that's taking electrical energy. That's what I forgot again. That's what electric motors do. They take electrical energy and then they convert it into mechanical energy. And it's generally spinny energy, right? Rotation. When you turn on a ceiling fan, it takes electrical energy, spins the fan. When you take the pool pump, when you turn that on, it just spins the impeller. When you have the little drone propeller motors, all they do is spin propellers. And so generally that's what electric motors do. Your blenders at home, they take electrical energy and they just convert it to rotational kinetic energy, essentially. So the opposite of that is how we generate electricity. To generate electricity, we essentially do the exact opposite. Instead of taking electrical energy and converting it to spinny energy, we take spinny energy and convert it into electrical energy. It doesn't have to be spinny, it just happens to be that's the most convenient way of doing it. And so to demonstrate how we can generate electric currents with magnets, I have a little setup here. Then I'll have to zoom in again. Again, sorry about this. This is a lot to juggle right now when making this video, so bear with me. Okay. So here, this is called, notice it says on it galvanometer. That just means it's there to detect electric current. It hasn't been calibrated into an actual ammeter, which is what we use to measure electrical current. So there's no units on it. It's just there to detect relative amounts of electricity. And then I have connected to it in a closed circuit, or at least it will be when I connect this, what is called a solenoid. And a solenoid is literally just a bunch of wire wrapped around an insulating core. So this plastic core, notice it's hollow. And so around that plastic tube, we got a lot, hundreds and hundreds and hundreds of coils of wire wrapped around it. And so if I take a permanent magnet, this permanent magnet, and then I just insert it within the magnet, within the solenoid, I see a deflection of the galvanometer. Okay. And notice if I reverse the direction that I'm moving it within, then the direction of the current actually changes. Now I have the south pole in it now. When I go in with the south pole, it goes this way. This way. When I go out with the south pole, it goes that way. If I do it with the opposite pole, the north pole, then it goes in the opposite direction. So again, the directions are very important here. If you want to know what direction the force is, what direction the currents, what direction the magnetic fields are, it's very important to know the right-hand rules in order to determine what those are going to be. Okay. So it turns out this isn't a very efficient way of generating electricity. And so what we use to really generate electricity are devices that will actually rotate. Just like we want electric motors to take electrical energy and convert it to rotating energy, rotating kinetic energy, we can do the opposite. We can take rotating kinetic energy like that and convert it to electrical energy. And so I have a little circuit set up here. I got 4 light bulbs all in parallel, as you'll notice as soon as I zoom in on it. So you got 4 light bulbs wired in parallel. And what's interesting is that this is an electrical generator. And all it is, it's just like an electrical motor. You have a bunch of coils of wire within an enclosure that has magnets. And so as you spin the magnet within the coil of wire senses a changing magnetic field. When the wire senses the changing magnetic field, that's when it generates electricity. Notice it's not generating electricity now because there's no motion happening. You actually have to do work. You can't get free electrical energy. You have to convert some other type of energy in the form of rotation to generate the electrical energy. But we can see that here, right? So this is an electrical generator. It operates on the principle of electromagnetic induction, and that principle just says that if a coil of wire senses a changing magnetic field, then an electric current will be generated within that coil of wire. If it is part of a closed circuit, you can't have it if I disconnect one of these guys, nothing happens. Okay, but if I connect them and now I got a closed circuit, I generate electricity. Okay, and I can do the same thing with a series circuit. So here I got 4 light bulbs in series, just to bring it back to our circuits unit. And notice they don't get as bright. They don't get as bright because I've increased the overall resistance of this circuit by having the light bulbs all in series. If you remember series resistors, their resistance, if you connect resistors or light bulbs in series, the resistance goes up for the whole circuit. If you connect them in parallel, then the overall resistance of the circuit actually goes down. And that's why these guys got brighter than those guys. Okay. All right. So that's how generators work. And it's kind of interesting because this is how power plants work. All power plants, with the exception of solar power plants, all power plants work on the principle of electromagnetic induction. They take spinny energy and they convert it to electrical energy just like that. Just like that. Let's do it so you can see it. And so, literally all power plants, with the exception of solar power plants, which uses physics that's actually vastly more complicated than what we're dealing with here. That's the photoelectric effect, stuff that Einstein figured out. Nuclear power plants, coal-fired power plants, natural gas-powered power plants, geothermal power plants, all those, and again, nuclear, I think I said nuclear. Wind turbines, windmills, they all produce electricity by taking some type of energy, converting it to rotating energy, having that rotating energy just spin big magnets within big coils of wire, and that's how we generate electricity worldwide. That's literally how we power the world. So in the hydroelectric dams too, if you've ever been on a dam, you got the hydroelectric dam, the water's up here on this side, but it's down here on this side. So the water flows down channels through the dam, and then it hits big paddle wheels that spin turbines that spin the magnets. And so that's how we get it there. With nuclear power plants, with geothermal power plants, with coal-fired power plants, all they do is they use all that energy generated in all those different ways to make steam, to convert water to steam, to heat up water, to make it steam. And then that steam is fed into turbine rooms that then spin turbines that spin big magnets within giant coils of wire that generate electricity. So all power plants actually work on that principle. Okay. All right. One last thing I want to talk about. You see the high voltage power lines around here, and then when you go farther out of town, you see the really tall, huge power lines that have crazy high voltage. We're talking over 100,000 volts on those power lines. If you were to connect your house or the school directly to the high voltage power lines, you'd have fires. It'd be very unsafe. You wouldn't want to do that. And so there's a device called a transformer that actually takes high voltage. It can do both. It can either take high voltage power, convert it to low voltage power, which happens when the voltage gets stepped down to go into our homes or our school. But we also have transformers that do the opposite. And so this is an actual transformer that was taken out of, I want to say a microwave, but I'm not sure. And all it is 2 different coils of wire. I got one down here that you can see, the other one up here that's actually wrapped in a material to insulate it from the other one. 2 coils of wire that are not in electrical contact, but they are around what's called an iron core. So what happens is that the electricity in one of the coils of wire is connected to the high voltage power lines. Not this transformer, but other transformers. But that voltage is actually, or that electricity is actually alternating current. So in this coil of wire, the current is going to constantly oscillate back and forth. And as it oscillates back and forth, it will form the magnetic field that we know, but that magnetic field will continually be reversed. It'll go back and forth because the direction of the electric current goes back and forth, which generates changing magnetic fields within the iron core. And since the other coil of wire is wrapped around that same iron core, that coil of wire senses that changing magnetic field, and through the process of electromagnetic induction, gets an electric current generated within it. And all you have to do is have different numbers of coils, or different numbers of loops in each coil, and depending on which one has more loops and which one's connected to the voltage source, then that determines whether we step up in voltage or step down in voltage. It's actually a very simple device, but it's very important because that's how, again, we take high voltage power from the power lines to low voltage power that we can wire our houses with. Okay, it's very important. All right. And I think that's about it. Let me just make sure I covered everything on this worksheet that y'all are doing. Yeah. And I'll end with this. I'll end with the experiment that started this all. Literally started everything. The experiment that when you consider the ramifications of it and its effects on human society and how our world works, probably the most important discovery of all time. And that was made, you read about it, or Mr. Luis taught you about it. Hans Christian Ørsted was the first one to notice. And the story is that he wasn't even trying to do it. He just had a compass needle on his desk when he was doing experiments with electricity, and he noticed. Now what I got here, this is just that compass needle I talked about earlier, but this is essentially a wire. And this little piece of plastic is insulation, so it's not going to, so it doesn't allow electricity to go from here to here. It's got to go around. And so you think of it as a wire, a single loop of wire around this magnetic compass needle. Okay. And so it was this discovery again that showed the relationship between electric current and magnetic fields, which paved the way for electromagnetic induction. So whenever I hit the switch here, turn up the voltage. Whenever I hit the switch here, I get electric current going towards you through the top and then back towards me through the bottom and then out. And again, we can use the right-hand rule to show, if I'm in the direction of the top current, creates a magnetic field that actually points this way within the loop. And then if I go down to the bottom and I'm moving this way, well, my fingers still curl around by the first right-hand rule. And so even the current in the bottom creates a magnetic field that points in the same direction. So when I run current through this, it should deflect in that direction. And sure enough, it does. Okay. And then if I reverse the direction just by reversing the wires, now the current is going in the opposite direction. And sure enough, we get an opposite direction magnetic field. Okay. Hopefully you can see that with my shirt. If you can't see that, here, let me do it again. There we go. Okay. So that's it. Hopefully I hit everything. I think I did. Yeah. And remember that the magnetic field generated by a current carrying wire makes circles around it, right? That's what the right-hand rule kind of shows you. The first right-hand rule. Oh, I forgot the electromagnet. Oh my gosh. Sorry. I blame my first period for that, for being so quiet. Just kidding, first period. All right. So here I got one of those coils of wire that's wrapped around the plastic. I got some paper clips here, not magnetic, not picking anything up. This guy's not magnetic, not picking anything up. But when I run electricity through this, that other right-hand rule tells you that you get a magnetic field through the center of the solenoid. And if I put a non-magnetized piece of iron, remember the video we watched that talked about the domains will all align with that magnetic field to generate quite a powerful electromagnet, which as you can see is pretty powerful. And as soon as I take the switch off, magnetism turns off. Okay. So that's an electromagnet. Again, the relationship between electricity and magnetism, very important. All this stuff, and again, going back to the single experiment or single discovery that electric current generates magnetic fields. Computers wouldn't work without this. Your phones wouldn't work without this. The electronics in your car, the sound systems that you listen to, the lights when you turn on light switches, none of that would be possible without knowledge and understanding of these effects. So that's it. Hope you have a good day. Sorry. Bye.